So just to start off in this lecture, we're going to review some of the calculations we did in the previous lecture. And so today we're going to look at, starting off, we want to know how much heat is absorbed when 87 grams of ice is heated from -7 to 16 degrees Celsius. So we have this ice, we want to heat it, we want to know how much heat it's going to need. And so some of the information it gives us the melting point of ice. It gives us the heat of fusion. Remember, the heat of fusion is the energy needed to convert 1 mole of ice into water. And it also gives us the specific heats of liquid and solid. So the first thing I always like to do when I'm doing one of these is to draw a little heating curve. And so a heating curve on the y-axis is temperature. On the x-axis is, you can say Q plus for Q added, or you can just write Q added. Because on a heating curve, we're adding heat and seeing what happens to our substance. So initially, we start at -7 degrees Celsius. And the way you know it's a heating curve is because we start at a low temperature and go to a high temperature. And so as you start adding heat from -7 degrees Celsius, the temperature increases as you add heat until you get to the first phase change, which will be at 0 degrees Celsius. So at 0 degrees Celsius, what we're going to see is we're going to see the solid get converted into a liquid. So we go from solid to liquid. Before 0 degrees Celsius, it's just a solid. When we get to 0 degrees Celsius, we go from a solid to a liquid, and note that there's no change in temperature when we're melting the solid. The temperature is constant. Next, after all the solid's been converted into liquid, the temperature increases again until our final temperature, which is 16 degrees Celsius, is met, because we don't go through another phase change, because the boiling point of water is 100 degrees Celsius. So this is what our heating curve is going to look like. And so at this slant, we're in the liquid phase. And so what you notice is on the slants, we're in one particular phase. On the plateau, we're going from one phase to another. So in order to calculate the heat that is absorbed, we have to determine the heat at 3 different areas on the graph. So we have Q1 and Q2, Q3. Now remember, for the slants, whenever you're on a slant, you're going to use the equation Q equals MC delta T. So anytime you see a slant, you're going to use Q equals MC delta T. Anytime you're on a plateau, you're going to use Q equals N times delta H. We'll explain what all those components are in just a moment. And so we're going to calculate 3 Q's. So Q1 is MC delta T. So M stands for the mass. So we have 87 grams. C is the specific heat. And for Q1, we're in the solid state. So you have to use the specific heat for the solid, which is 2.09 times 2.09. And now when we get to delta T for the first Q, it's only the delta T of the solid. So remember, delta T is final minus initial. So it's 0 minus a -7. And that's how we calculate the Q for the first stage. So the first stage, we're only a solid, and we're increasing the temperature. Now for Q2, remember, it's N times delta H. N is the moles. So we have to find the moles of ice. So it's going to be 87 divided by its molar mass, which is 18. Now, when you're doing these calculations, I mean, you can keep 3 or 4 significant figures should suffice. And so again, that's the moles of ice. We're going to need it for Q2 because in Q2 we're going from a solid to a liquid. We're going to use the delta H of fusion. Now Q3, we're going to do the exact same thing we did for Q1 for Q3, except now we're in the liquid state. So it's going to be the same mass, but for the specific heat, we're going to use the specific heat of the liquid, because in Q3 we're in the liquid state, and then it's going to be the temperature change of the liquid, so 16 minus 0. And so this is how you set up these 3 different Qs, and now we can determine the energy of each step. Just double check my work. Okay. So when we get to this point, you should notice that Q1 and Q3 are in joules, Q2 is in kilojoules. So with Q1 and Q3 in joules, what we need to do is convert those to kilojoules by dividing by 1,000. So when we take Q3 and divide by 1,000, we get 6. And we do the same thing for Q1 because you have to have them in the same units. So now we have all 3 Qs in the same unit. We can add them together to get Q total. So I get So I get 36.22 kilojoules. So in the second example, here we want to know how much heat, calculate the heat released when 150 grams of ethanol at 85 degrees Celsius is converted to solid ethanol at a negative 114 degrees Celsius. So the way we know this is a cooling curve is multiple reasons. One, it says how much heat is released. So if we're releasing heat from a substance, that means that we're cooling it. Secondly, our initial temperature is higher than our final temperature. So this is going to be a cooling curve. Likewise, it gives us the boiling point of ethanol. It gives us the heat of vaporization, which is the amount of energy needed to convert a mole of liquid into a mole of gas. Delta H of fusion is the amount of heat to convert a mole of solid into a mole of liquid. And then it gives us the specific heat of the gas and the liquid. Now, as I mentioned in the previous lecture, the reason that the heat of vaporization is so much larger than the heat of fusion is because when you go from a liquid to a gas, you're breaking the attractive forces that hold the molecules together. So it takes a lot of energy to break it. Whereas in melting, you're just weakening the attractive forces. So now I'm going to come over here and draw my cooling curve. So again, the y-axis is T. Now for the x-axis, it's Q remove, or I'm going to put a negative Q, meaning that we're removing heat. So we're going to start at 85 degrees Celsius. And as we remove heat, the temperature decreases until the first phase change, which in this case is 78.5, because that's the boiling point of ethanol. I'll just put 78 for now. And so at the phase change, we're a plateau. There's no change in temperature. And we're going from, in this case, we're going from a gas to a liquid. So before that, we're only a gas. But when we get to the boiling point, we're going to go from a gas to a liquid. And then the temperature starts decreasing again until it gets to the next phase change, which is, oops, I forgot to put it, but the melting point of ethanol is negative 114 degrees Celsius. Something I forgot to add. Let me put that here. And for everything other than water, you're going to be given the melting point, boiling points of the substance. So water is the only one you should know. Other than that, it'll be given to you. And so at negative 114, all we're doing is we're going to go and do a phase change. Then we stop because we want to stop at negative 114, which is the freezing point of ethanol. So at this slant here, we're in a liquid, and then when we get to the plateau, we're going from a liquid to a solid. So again, we want to know basically how much heat is released when we take a gaseous sample of ethanol and freeze it, because the freezing point is negative 114 degrees Celsius. So here we have 1 Q, 2 Qs, the third Q, and the fourth Q. So we have 4 Qs to calculate. Now remember, on these slants or diagonals, we use Q equals MC delta T. For the plateaus, we use Q equals N times delta H. And so again, before we begin, since we're going to need moles, I'm going to go ahead and calculate the moles of ethanol. And the formula for ethanol, if you're interested, is C2H5OH. So 24 plus 16, 6. So the molar mass is 46. So we get about 3.26 moles of ethanol. Now the reason I already calculated moles is because for Q2 and Q4, we're going to have to be calculating the moles, or in the cube, from the moles. So now I'm going to set up my Q equations. So Q1, here we're only in the vapor state or gaseous state, so we're going to need the mass of our gas. We're going to use the specific heat of the gas and the temperature change of just the gas. So be 78.5 minus 85. And notice here that our delta T here is going to be negative, because remember, delta T is T final minus T initial. Now we do Q2. For Q2 is the number of moles times the, now what's occurring at Q2? We're going from a gas to a liquid. So what is occurring is we're doing condensation. But we don't have the delta H of condensation, we have the delta H of vaporization. Vaporization is when you go from a liquid to a gas. Condensation is when you go from a gas to a liquid. So the delta H of condensation is just the negative of the delta H of vaporization. So our delta H of condensation would be negative 40.5. And that's very important because it's not vaporizing, we're condensing the gas into a liquid. So we need the delta H of condensation, which is the negative of the delta H of vaporization. Q3, here we're in the liquid state. So again, we need the mass of the liquid. We need the specific heat of the liquid and the temperature change of just the liquid. So it's negative 114 minus 78.5. And then when we get to our last stage, again, we're going to be using since it's a plateau, we're going to be using N times delta H, so moles times delta H. Now here we're going from a liquid to a solid, so we're freezing the liquid. Now what we have is delta H of fusion, which is when we go from a solid to a liquid. Now if we're going from a liquid to a solid, we need the delta H of freezing. What we have is the delta H of fusion. In order to get the delta H of freezing, we need to make the delta H of fusion negative. It'll be negative 4.60. And just to remind everyone is that these delta H's of freezing and condensation you will not find in a book. You only find the heat of vaporization and heat of fusion, and then you have to remember to make them negative to get the heat of condensation or heat of freezing. So now we can, as they say, plug and chug. Negative 15, and that's in joules. Double check. Okay. Negative 132. Okay, now we do Q4. All right, so now again, you'll, oh, made a typo. Let's see, put a negative sign. So now you'll see that Q2 and Q4 are in kilojoules. And again, the reason they're in kilojoules is because the delta H's are in kilojoules. And Q1 and Q3 are in joules. And the reason they're in joules is if you notice the specific heats are in joules. So we're going to convert the Q1 and Q3 into kilojoules by dividing by 1,000. So now we have all the Q's in kilojoules. We can get our Q total. Write that again. Double check my work. So you see that we released 219.2 kilojoules of heat. Now, if you were solving this problem on the homework, for example, if it said released in the problem, you don't have to put the negative sign. So like on the Connect homework, if it says, how much energy is released, then it's not required to put the negative sign in it. Also in the homework on the weekly homework, you read the question, it may say you may need it or you may not need the negative sign. Because release infers that it's going to be negative. And so what you'll notice is that Q2 requires the most, or releases the most energy, because what's happening is when you go from a gas to a liquid, you're reforming those attractive forces, which makes the molecule more stable, or makes the substance more stable, releasing energy. So that's why Q2, when you go from a gas to a liquid or liquid to a gas, that's going to be the step that consumes the most energy in the process. Oh, excuse me. I got a little bit ahead of myself. Now we're going to be discussing, we talked about, phase changes going from a gas, liquid, and solid. We're going to actually discuss a little bit about the different types of solids that we can have. And so there are four main groups of crystalline solids. Now again, crystalline solid means it has an intricate network of atoms or molecules in the structure. And there are four types of crystalline solids. So the first type is a metallic solid. And again, metallic solids are just metallic elements. So any element on the periodic table that is a metal is a metallic solid when it's just that element. So for example, copper is a metallic solid. Iron is a metallic solid. Silver is a metallic solid. So again, these elements, when they're completely by themselves, are metallic solids, like your transition metals, your alkaline earth metals. Those are metallic solids. And so what they have is an extended network of atoms that are held together through what's referred to as metallic bonding. And this metallic bonding is very strong, which gives rise to metals having very high melting and boiling points. So again, metallic solids are solids that are pure metals on the periodic table. So silver, gold, copper, tin, lead, these are all types of metallic solids which are held through metallic bonding. Next we have ionic solids. Now with ionic solids, here we have ions being held together through ionic forces. And so the way you know an ionic solid is it's an ionic compound. So if you see the formula of a metal and a non-metal, it's a ionic solid. So again, a metal and a non-metal means you have an ionic solid present because you have cations and anions. And these ionic forces that hold the ions together is very strong, and that's why ionic solids mostly have high melting and high boiling points, because of the very strong attractive forces that hold the ions together. So again, any ionic compound, aka metal and non-metal in the formula, are going to have ionic forces. They're going to be an ionic solid. There are a few exceptions that have ions, but they don't have metals in it. For example, if you have an ammonium compound is an ionic solid, but it won't show metals in the formula because ammonium is a polyatomic cation, and majority of polyatomic anions only contain nonmetals. So that's the only really exception when we're talking about ionic compounds. But other than that, if it has a metal and a nonmetal in the formula, it's going to be an ionic compound, which is classified as an ionic solid. And these are held together through ionic forces, cation and anion, positive and negative. The third type of solid, and this third type is like a very a very private club of solids. And these are referred to as covalent network solids. So what a covalent network solid is that it's a solid that is one big molecule. So all the atoms are held together by covalent bonds. So some examples of network covalent solids are things like carbon diamond, carbon graphite. They're actually one big molecule, if you want to give that word, of carbon, or one big solid of carbons that are covalently bonded to one another. So if you know the classic view of carbon graphite is it forms layers, and then carbon diamond forms intricate three-dimensional structures. And so for silicon, usually like silicon dioxide is a network covalent solid, and those are probably the three most common covalent network solids. It's a very exclusive club of solids. Not many fall in this category. Again, we're talking about carbon graphite, carbon diamond, silicon dioxide, like quartz, not glass. Now, glass is not a covalent network solid. Quartz is a big solid of silicon and oxygen bonds, and it's a covalent network solid. So not many, there's only like 3 or 4 well-known covalent network solids, not many. And lastly, we have molecular solids. Now, molecular solids are solids that only have nonmetals in the formulas. So if you look at a formula and there's only nonmetals present, then that means it's a molecular solid. And so these are solids that have molecules that are held together through attractive forces, which we'll learn about later, that are called intermolecular forces. So for example, water is a molecular solid, carbon dioxide is a molecular solid, because all of these have nonmetals in the formula. Fluorine gas, F2, is a molecular solid. So again, when you look at a solid and all you see are nonmetals, you have to see at least more than one nonmetal. It won't be by itself. It'll be either 2 or more nonmetals bound together. Then it's a molecular solid, and these are held together by attractive forces, which we refer to as intermolecular forces. And that's actually at the latter part of chapter 7 or chapter 12 that we talk about. So out of all of these, the ones with the strongest forces holding the atoms together or ions together is covalent network solids, and the weakest is probably the molecular solids. Now, there is one other group of solids that doesn't get much attention, but this is the group 18 elements. So we're referring to the noble gases, and noble gases are referred to as atomic solids. So noble gases and the interesting thing about noble gases or atomic solids is it's just made up of one atom. So for example, helium, argon, krypton, neon, etc. So only noble gases can be atomic solids, and these have very weak attractive forces, because we all know that helium, how do you buy helium? If you buy it as a gas, and since it's a gas at room temperature, you know it has very weak attractive forces. And so these are the different types of solids you can have. You can have metallic solids, which are going to be your metals found on the periodic table, just the metal, nothing else. You can have ionic solids, which contain typically a metal and a non-metal, which are held together by ionic forces. You can have covalent network solids, which is an exclusive club of a very few compounds such as diamond, graphite, and maybe quartz. And then molecular solids, which the key thing is that the compound or substance is made up only of nonmetals, and these are held together through attractive forces. And then lastly, atomic solids, which are your noble gases. So only noble gases can be atomic solids. Again, that's like helium, argon, krypton, neon. So this is just what we just talked about, but a little bit more in description-wise that you can read about later. But it's atomic solids are individual atoms held by very weak attractive forces called dispersion forces. Molecular solids are molecules held together by different types of attractive forces, aka intermolecular forces. Ionic solids are involving cations and anions. Molecular solids just have metallic atoms and have an organized, what we call crystal structure. And then network covalent solids involve just covalent bonding and form intricate types of structures. So besides the types of crystalline solids, which we just talked about, we also have amorphous solids. And the difference between an amorphous solid and a crystalline solid, so a crystalline solid, we had those 5 categories. We had, for crystalline solids, we had metallic solids, ionic solids, covalent network solids, molecular solids, and atomic solids. And these have what we call a crystal lattice, which is a very ordered structure. If you imagine Legos, imagine the same color Lego and the same shape Lego being repeated in 3 dimensions. That's what a crystal lattice looks like. So each Lego is a lattice, and so you just move the Lego in 3 dimensions and you get your crystal or crystalline solid. Now, amorphous solids don't have any of that ordering or repetition. And so crystalline solids, as you see on the left, have a very well-defined, if you want to call it, repeating Lego. You imagine this is a Lego, gets repeated in 3 dimensions. Whereas, quartz is not a crystalline solid, but SiO2 is, silica, sorry. Quartz is, or quartz glass is what we refer to as an amorphous solid, which is something that doesn't have a very ordered structure. So things like glass, rubber, coal, those are amorphous solids. So they're not crystalline. So you imagine looking at salt. You buy salt from the store, it has these tiny crystals that make up salt. Salt is a crystalline solid. And people actually do research on these repeating, we want to call them Lego blocks, to see what the block is made up of. And that's where we use this technique called X-ray diffraction. So again, solids, we have 2 types, crystalline and amorphous. Crystalline solids, very well defined, have the same repeat unit, the same Lego that goes in 3 dimensions. And we discussed the different types of crystalline solids. Again, quartz glass, I apologize, it's an amorphous solid, not crystalline. But SiO2 or silica is a crystalline solid. And that is a SiO2 silica is a network covalent solid. And so when we talk about crystalline solids, we talk about that repeat unit or that Lego. And that Lego is composed of what we call lattice points or repeat units in the box. And so we refer to this box in chemistry terms as a unit cell. So imagine this unit cell, I'll call it, similar to a Lego. It gets repeated throughout the entire solid, and that's where we get our crystal lattice. Imagine the same Lego being replicated in 3 dimensions. And this crystal or this unit cell has certain parameters for it. So for example, in this illustration here, we have the lengths of the unit cell, which are A, B, and C, and we have the angles of this unit cell, alpha, beta, and gamma. So depending on how these parameters are, we can have different shapes of the unit cell or different shapes of the Lego. So depending on the solid, it may have a different shape than another solid. So for example, the shape of the unit cell of sodium chloride is different than the shape of the unit cell of the common ingredient acetylsalicylic acid in aspirin. So they're both crystalline solids, but the repeat unit, the box that or the Lego that gets repeated, is a different shape. And so different solids have different shapes, which have what we call different constraints on these parameters of the box. So there are, as I said, there are many different types of boxes that we can have for unit cells, and that's dependent on the constraints of the lengths and the angles of the unit cell. And so for all crystalline solids, there are 7 types of what we call unit cells, or different types of boxes. And as you can see, depending on what is constrained, we get a different type of box. So the box or the unit cell with the most constraints is cubic. So in a cubic unit cell, all the lengths equal each other and all the angles equal 90. For example, sodium chloride is in a cubic unit cell. So the box of sodium chloride has all the same lengths and all the angles are 90. And then we go to things like tetragonal. So tetragonal is very similar to cubic, except that A and B sides are the same, but C is different. Again, all the angles equal 90. We go to orthorhombic. None of the lengths are the same, but all the angles are 90. Now with something called hexagonal, we have a difference of angles and lengths. So A and B are the same length, but C is something different. And alpha and beta are 90, but gamma is 120. So depending on how the solid crystallizes will determine what type of unit cell they fall in. Rhombohedral is kind of like cubic's cousin, where A, B, C are the same, but you see alpha, beta, gamma are the same, but not 90 degrees. And the two last ones are monoclinic. You see monoclinic has no side that's the same as the other, and alpha, gamma equal 90, and beta is some other angle. Now you heard me mention the example where we had sodium chloride and aspirin, or acetylsalicylic acid. They crystallize in different unit cells. Again, sodium chloride crystallizes in the cubic unit cell, whereas acetylsalicylic acid actually crystallizes in what we call the monoclinic unit cell. So different solids crystallize in different types of unit cells. And then triclinic is with no constraints on the lengths or the angles. You may say this is a lot, but actually with most crystal structures of molecular solids, there's only like 3 main unit cells, and that is triclinic, monoclinic, and orthorhombic. So most molecular solids, when you crystallize them, will crystallize in one of those 3 unit cells. So again, sodium chloride is a cubic, whereas acetylsalicylic acid, which is an aspirin, monoclinic. Okay. Now we're just going to spend a little bit more time on cubic unit cells because they're very simple and easy to understand, because again, all the lengths and angles are the same. And there are 3 types of cubic unit cells depending on how the atoms are arranged in the box. So if we take a look at this, the first one is called a primitive unit cell, and usually they use the symbol P to indicate this unit cell. Now for a primitive unit cell, you'll notice that there is a lattice point, or atom, ion, whatever, I guess atom in this case. There is a lattice point on every corner of the cube. So every corner of this Lego has a lattice point, aka an atom. So if you imagine this in 3 dimensions, one lattice point on the corner would be touching how many other boxes? So if you have one lattice point on the corner in 3 dimensions, it'll actually be touching 7 other boxes next to it. So since 7 other boxes are touching it, that atom is actually 1/8 of an atom when it's on that corner for one box. And so if you notice here, we have 8 lattice points, each one occupying an eighth. So we have 8 atoms times 1/8 equals 1. So a primitive cubic unit cell only has 1 atom in it because each corner is 1/8 of an atom. So whenever you see a question about a primitive cubic lattice cell, it says how many atoms are in a primitive cubic unit cell, it's just 1. Next we have body-centered cubic lattice, and for body-centered they typically use the symbol I. So I refers to body-centered cubic lattice. So just like with the primitive, we have an atom on each corner, and we have an atom in the center of the box. So if you can imagine, now we have 8 corners or 8 atoms occupying 1/8 of an atom plus 1 atom in the center. This has a total of 2 atoms or 2 ions. It could be ions too, because you could have something like sodium chloride, for example, that could crystallize in this. So with primitive, you cannot have ionic compounds because there's only 1 atom or 1 lattice point. With body-centered, you can have atoms or you could have ionic compounds. Now lastly, with face-centered, if you notice the difference here, we have an atom on every corner, and we have an atom on every face of the crystal, of the box. And so each face of the unit cell touches another face on another unit cell. So when you see an atom on a face of a unit cell, it's actually 1/2 of an atom. And so if we look here, we have 8 atoms on corners, each one is 1/8, plus we have 6 atoms on the faces, because there's 6 faces on a cube, each one occupying a half, so we get a total of 4 atoms. And so face-centered cubic can contain or contains 4 atoms or 4 lattice points, and it's usually denoted the symbol, as you can imagine, F. So we have primitive, which only has 1 lattice point, aka 1 atom. We have body-centered, which has an atom on every corner and 1 atom in the center, which has a total of 2 atoms or 2 ions. And then we have face-centered, which has an atom on every corner and an atom on every face. So that's a total of 4 atoms. And so this is how you can determine the number of atoms or ions in a unit cell, is by knowing the number of lattice points in that cubic unit cell. And so just to show you what a non-cubic unit cell looks like, and this is not going to be on a test or nothing, but this is just cool stuff to look at. So here we have this compound 1,1,4-iodo-phenylurea, and it's a monoclinic unit cell. And so within the unit cell, you have the basic repeat unit that gets repeated in the unit cell. So not only do you have the unit cell that gets repeated, but you have the entity inside the unit cell that gets repeated, and then the whole box gets repeated. So the portion of the unit cell used to generate the rest of the box is called the asymmetric unit. And so this box actually has 2 molecules in it. And this little blue line, it's hard to see, but this little blue line is the attractive forces between the oxygen on one molecule and the hydrogen on another. And that's what holds those 2 molecules together, is that attractive force. And so that's the box that gets replicated in 3 dimensions. And so here's just a zoom up where you can see the symmetry, or what was used to generate that second molecule. So what they did is they rotated the first molecule. If you look at this molecule here, they rotated it 180 degrees, and then they moved it halfway through the box, and that's how they got the second molecule. And this is what I do when people send me their crystalline solids. I tell them what's inside the box. I tell them this right here. And from that they can design drugs or look at hydrogen storage better, for example. And so this is just kind of an overview. So again, the types of crystalline solids, we have atomic. These are going to be your group 18 elements. Physical properties, very poor, very low melting points, very weak attractive forces called dispersion forces. Molecular solids, if you remember from CP1, we talked about polar and nonpolar compounds. Molecular solids can be polar and nonpolar. And we'll talk more about that when we talk about the different types of attractive forces. But molecular solids can have different attractive forces such as dispersion, dipole-dipole, hydrogen bonding, relatively moderate melting points, but they're poor thermal and electrical conductors. So these are like the two weakest here. Atomic is the weakest, but then molecular. Then we have ionic, which has ionic forces, very high melting points, very hard, good thermal and electric conductors. Metallics, again, those are made up of atoms, metallic atoms, and they have a range of soft to hard depending on the type of metal you use. For example, sodium is very soft, whereas zinc or iron is very hard. And then lastly, we have the network covalent atoms, network covalent solids, which are made up of atoms, but it's like one big structure of atoms held together through covalent bonding. Oh, and I was right. Silicon dioxide quartz is a network covalent solid. It's just when it's glass, it's not. So quartz by itself is a network covalent solid, but quartz, when it's referred to as glass, is not. And you see quartz has a very high melting point, and so does diamond as well. They actually use diamond drill bits when they're drilling into the center of the earth because of its high melting point. And this is just interesting here to show you the difference between graphite, which is very soft, and diamond, which is very hard. And you know, as everyone says, shiny like a diamond. Well, diamonds are very nice looking solids because of one difference. And let me show you that difference. So here for graphite, if we have a carbon atom, it's made up of carbon atoms, it looks like this. So graphite, the repeat unit, is a carbon with a double bond and two single bonds. This is graphite. The only difference between graphite and diamond, the difference between something very soft and something very hard, is one single bond. So diamond actually has 4 single bonds on the carbon. So just by replacing one of those single bonds with a double bond, you go from something that is very hard to something that is very soft. Something that everyone likes to something that no one cares about. All just based on going from 4 single bonds to 1 double bond and 2 single bonds. So on that note, that concludes this lecture over the types of crystalline solids.